Welcome to the Deep Dive. You're here because, well, you want to get the important stuff, understand it quickly, thoroughly, really get those aha moments without getting bogged down.
Exactly.
Today, we are diving deep into hydrogen, specifically its potential, as a low-carbon energy carrier, helping us move towards a cleaner future.
Yeah, and there's a lot of global interest right now. I mean, you've got these big international partnerships, like the one with 20 countries focusing on hydrogen and fuel cells.
Right.
And the European Commission is pushing hard. Plus, you see research groups popping up everywhere. It's definitely not just a flash in the pan.
So our mission today is to cut through some of the noise, extract the really key insights about hydrogen's role,
Right.
in decarbonization. We'll start with the basics. What actually is hydrogen? Then look at how it's made, stored, moved around.
And crucially, how it might fit into cleaning up the power sector.
Yeah, exactly. And we'll touch on other uses too, the roadblocks, what policymakers are doing. Okay, let's jump in. Fundamentals first. What is hydrogen?
Right. Well, at its absolute core, it's the simplest element there is. Number one on the periodic table, symbol H.
H.
Usually, though, it hangs out as a molecule, H2. And that's a non-toxic gas at room temperature and normal pressure.
Okay.
Interestingly, it only turns liquid at incredibly cold temperatures, like minus 423 Fahrenheit, really, really cold.
Wow.
And
Right.
you find it everywhere, but locked up in compounds, water, obviously H2O, but also ammonia and hydrocarbons like natural gas, coal, oil. It's in all of those.
So it's all around us, but kind of hidden. Now, how are we actually using it today? Because like you said, it's not like I'm filling my car with hydrogen easily.
Not yet, no. Right now, the vast majority globally is used for big industrial stuff. Oil refining, that's about a third of all hydrogen produced.
A third, okay.
Then you've got ammonia production, that's key for fertilizers and methanol production. They're each around 27% roughly. Steelmaking uses a smaller chunk, maybe 3%. In the US, it's a pretty similar picture. Refining, ammonia, methanol are the big ones. Then maybe 10% for things like treating metals, food processing, other bits and pieces.
Okay.
Now, it can be used as a fuel for electricity, transport, even heating buildings. That's where the low carbon potential comes in. But those uses, still pretty limited today. It's mainly an industrial ingredient for now.
An industrial workhorse, but maybe with bigger ambitions. Okay, so it's an industry. But we keep hearing energy carrier. What does that actually mean? We don't just dig up hydrogen, right?
Exactly right. It's not a primary energy source like the sun or wind or coal. You have to make it using energy from somewhere else.
Oh, okay.
That's why it's an energy carrier. Kind of like a battery, You put energy in to charge it up, then you can use that energy later.
So you make the hydrogen.
You make it, then you can store it, move it, and use it, maybe in fuel cells or to make ammonia or biofuels, or even for welding and stuff in industry.
And the key thing is how clean it is depends entirely on how you made it in the first place.
Precisely. The production method dictates the carbon footprint.
Which brings us to the colors. Green hydrogen, blue hydrogen, gray. Sounds like we're choosing paint. What's going on there?
Huh. Yeah, the colors are basically a shorthand. They try to differentiate the production methods and sort of the greenhouse gas emissions tied to them.
Sort of.
Well, the big problem is there's no single universal standard for these colors, so it can get confusing, honestly. Leads to miscommunication sometimes.
Okay.
Ideally, we should really just be talking about the actual carbon intensity. How many kilograms of CO2 per kilogram of hydrogen. That's the real measure. But the colors are widely used, so.
So we should probably know the main ones. Give us the quick rundown.
Okay, you'll hear black or brown hydrogen. That usually means it's made from coal using gasification, high carbon emissions there.
Right. Black, brown from coal.
Then there's gray hydrogen that's typically made from natural gas, usually steam methane reforming, or SMR, without capturing the CO2 emissions. That's most hydrogen today, actually.
Okay. Gray from gas, no capture.
Then blue hydrogen. Also starts with natural gas and SMR, but this time they add carbon capture and storage, CCS, to trap the CO2.
So that's lower carbon.
Well, it's intended to be lower carbon, but a major concern is methane leakage, methane being a potent greenhouse gas during the natural gas extraction and transport before it even gets to the hydrogen plant.
Ah, the upstream emissions of it.
Exactly. And then you have green hydrogen. That's one getting a lot of excitement. It's made using electrolysis.
Splitting water?
Splitting water, yeah, using electricity generated from renewable sources like solar or wind. So ideally, zero emissions.
That sounds like the goal.
It is. There's also pink, or sometimes purple or red hydrogen, which uses nuclear power for the electrolysis. Still low carbon. So yeah, colors give a hint, but the carbon intensity number is what really matters.
Got it. Focus on the actual emissions, not just the label. Okay, we know what it is, why we care. Now, how do we actually make this stuff on a large scale?
Right. So today, about 80% comes from plants built specifically to make hydrogen, dedicated plants.
Huh.
The other 20% or so is actually a byproduct, coming from other industrial processes like chemical plants or refineries.
Interesting. And for the dedicated production, what are the main ways?
There are really four main methods that dominate. Number one, by far, is steam methane reforming, SMR.
SMR. We mentioned that for gray and blue.
Exactly. It accounts for something like 3/4 of global dedicated production, and in the US, it's massive, like 95%.
Wow. How does it work?
It's a mature technology. You take high-temperature steam, react it with methane natural gas over a catalyst that gives you hydrogen, carbon monoxide, CO, and some CO2.
Okay.
Then there's usually a second step, the water-gas shift reaction, where that CO reacts with more steam to make more hydrogen and, well, more CO2.
So CO2 is a definite byproduct.
Yes. And then you need to purify the hydrogen, usually using something called pressure swing adsorption, PSA, to get rid of the CO2 and other stuff. You can actually use other fuels too, like ethanol or propane, but methane is dominant.
Okay, SMR is king right now. What's number two?
That would be coal gasification. Remember, black or brown hydrogen, this is it.
Right.
You partially burn coal with a catalyst, creates heat, chemical reactions happen. You end up making CO2, which reacts with more coal to make CO.
Right.
Then, similar to SMR, that CO goes through the water gas shift with steam to make hydrogen. And again, you need purification. Globally, this is maybe 23% of dedicated production.
So the top two methods rely heavily on fossil fuels. What about the cleaner options?
That brings us to electrolysis, the water splitting.
Green hydrogen source.
Potentially green, yeah. If the electricity is renewable, you use electricity in a device called an electrolyzer to split water, H2O, into hydrogen, H2, and oxygen, O2.
How common is that now?
Tiny fraction, actually. Less than 0.1% of dedicated production currently, but huge potential, obviously.
Right.
Inside the electrolyzer, you have an anode and a cathode in water, sometimes with an electrolyte added. Current flows, splits the water. There are three main types people talk about. Alkaline electrolyzers are the most mature, been around longest, make up most of the installed capacity today.
Okay.
Then PE, proton exchange membrane. These are gaining ground fast. They're more flexible, respond quickly, getting bigger too.
TEM. Flexible.
And the third is solid oxide electrolysis cells, SOEC. These are newer, operate at high temperatures. They have this interesting potential to run in reverse, like a fuel cell, generating electricity from hydrogen, but still more developmental.
Interesting. Okay, SMR, coal gasification, electrolysis.
Yeah.
What was the fourth one?
Methane pyrolysis. This is more cutting edge.
Pyrolysis. Heat decomposition.
Exactly. You heat methane really hot without oxygen, and it breaks down into hydrogen gas and solid carbon, like carbon black or soot.
Solid carbon, so no CO2 gas.
Potentially much less direct CO2 emission, yeah. The carbon comes out as a solid byproduct you could maybe even use. But there are challenges. High temps needed, getting pure hydrogen, handling the solid carbon. It's not quite there commercially yet.
So a range of methods. What about the all-important cost? How do these stack up?
Cost is complicated. It really depends on a bunch of things. The upfront capital cost of the plant, obviously, O&M costs, how efficient the process is, how much you run the plant,
Makes sense.
and crucially, the cost of your input fuel or energy. Is it cheap natural gas? Is it expensive electricity? That's a huge driver.
So what's cheapest today?
Generally, SMR using natural gas without carbon capture, gray hydrogen, that tends to be the lowest cost, assuming gas prices aren't sky high. The gas cost itself can be like 45–75% of the total cost.
Right, so it's very sensitive to gas prices.
Very. For coal gasification and electrolysis, the upfront capital cost is a bigger chunk, maybe half the total cost. So lots of R&D is trying to bring those capital costs down.
And green hydrogen, the renewable electrolysis.
That's generally the most expensive option right now, which is, the main barrier to scaling it up really fast near term, even though it's the cleanest.
Costs need to come down. You mentioned electrolyzer tech is evolving. Where are we with actual deployment? How much is out there?
Globally, it was around 300 megawatts installed by mid-2021. In the U.S., as of mid-2022, maybe 18.5 megawatts installed, but a lot more planned, over 600 megawatts announced.
So growing fast, but from a small base.
Exactly. Alkaline is the mature one. PEM is getting deployed more, from small kilowatt up to megawatt scale. Even bigger ones, over 10 milliW, are being developed. Solid oxide is still early days, not really commercial yet.
And there are standards for these things.
Yeah, there are ISO standards like ISO 22734 for electrolyzer hydrogen generators. They're even updating them now to cover testing for grid services.
Grid services, we'll come back to that.
Yeah,
So where does it make sense to make hydrogen cost effectively? Does geography matter?
hugely. It boils down to energy input costs. Got cheap natural gas, SMR is probably cheaper there.
Okay.
Got abundant, cheap solar or wind, then electrolysis could be your winner long term. The IEA, International Energy Agency, points to places like South Asia, Australia, the Middle East, parts of the US and China, North Africa, areas with great renewables potential, as promising spots for low-cost, low-carbon hydrogen from solar and wind.
Okay, so location matters for production cost. Now, say we've made it. How do we store this stuff? You mentioned hydrogen is tricky.
It is. Low energy density by volume is the big one. It takes up a lot of space for the energy it holds compared to, say, natural gas or gasoline.
So what are the options?
Well, you can store it directly either as a compressed gas in tanks, which is common for smaller amounts, or as a cryogenic liquid, which requires those super cold temperatures.
Tanks or liquid, okay?
For really large-scale, long-duration storage, the best bet currently seems to be underground geological storage. Salt caverns are ideal. They're big, impermeable.
Salt caverns, like underground caves.
Basically, yeah. Huge underground spaces leached out of salt deposits. But they're not everywhere, geographically limited, so research is looking at storing it in other things like depleted gas fields or aquifers.
So researching those.
Yeah. And because direct storage is challenging, people are looking hard at converting hydrogen into other things that are easier to store and transport.
Like what?
Ammonia, NH3, is a big one. It's already traded globally. Or you can combine hydrogen with carbon to make synthetic methane or other liquid fuels. Or bond it to liquid organic carriers, special molecules that soak up hydrogen.
So convert it, store the new thing, then maybe convert back.
Exactly. If you need pure hydrogen at the end use, you need an extra step to get it back out, which adds cost and reduces overall efficiency. But it might be worth it for long distances or long-term storage.
Storage is complex. What about moving it? Transportation.
Right now, most hydrogen is used pretty close to where it's made, on-site or nearby.
Okay.
But to move it further, for smaller amounts, you use tube trailers, big bundles of high-pressure gas cylinders on a truck. Carries maybe up to a ton.
Okay, trailers for gas.
Or liquid hydrogen tanker trucks. They can carry more, maybe 4 or 5 tons because liquid is denser.
Liquid tankers.
For really big volumes and where you have steady demand, dedicated pipelines are the most efficient. Like natural gas pipelines, but needing different materials or coatings for hydrogen, they can move hundreds of tons a day.
Pipelines for bulk. What about ships?
Shipping is pretty uncommon right now. But there are early projects looking at shipping liquid hydrogen or ammonia, especially for international trade. Japan is keen on this.
So the best way depends on how much and how far.
Yeah, scale and stability of demand are key.
Okay, production, storage, transport. Now let's really focus on the power sector. How can hydrogen help clean up our electricity grids? That seems like a huge potential application.
It really is, especially as we add more renewables like solar and wind. Their output varies, right? The sun sets, the wind drops.
The intermittency problem.
Exactly. And that's where long-duration energy storage becomes critical, storing energy for hours, days, even weeks or months.
And hydrogen can do that.
That's the idea. When you have excess renewable electricity, say, midday solar production is booming instead of just curtailing it, throwing it away.
You use it to power electrolyzers.
Right. Make hydrogen. Store that hydrogen maybe in those salt caverns or convert it to ammonia. Then later, when renewables are low but demand is high, maybe a winter evening.
You turn the hydrogen back into electricity.
Precisely. Using fuel cells or hydrogen-ready gas turbines or other methods, it acts like a massive clean battery, potentially storing energy seasonally.
Seasonal storage. That's the holy grail for renewables.
It really could be. And yes, salt caverns are limited geographically, but research is pushing on other storage options that could work almost anywhere.
Okay, so you've stored the hydrogen. How do you get power back out? What are the main technologies?
There are a few key ways. First, fuel cells. We touched on them. They electrochemically combine hydrogen and oxygen, make electricity and water. Very clean at the point of use.
Right. High efficiency potential, too.
Good efficiency, yeah, 40–60%. Potential for backup power, remote power, maybe even large-scale grid power eventually.
Yeah.
But cost is still high compared to, say, a gas turbine. R&D is working hard on that.
Okay. Fuel cells are one. What else?
Combustion gas turbines. like the turbines in current natural gas power plants, but designed or modified to burn hydrogen, either pure hydrogen or blended with natural gas.
Are those available now?
They are commercially in some places. Manufacturers are offering turbines capable of handling blends and aiming for 100% hydrogen capability.
But blending has limits.
Yeah, there are limits on how much hydrogen you can safely put into existing natural gas pipelines. And existing turbines definitely need mods for high blends or pure hydrogen. There's also research into turbines that burn ammonia directly.
Ammonia turbines. Interesting. Any other options?
Well, people are looking at co-firing ammonia in coal plants or using ammonia in specialized fuel cells. This is more R&D and demo stage.
Well, pros and cons there.
Could potentially be lower CO2 than even natural gas turbines, depending on how the ammonia is made. But concerns exist about ammonia slip unburnt ammonia, which is toxic and not AX emissions. Needs careful management.
So lots of technological pathways, but cost keeps coming up.
Yeah.
What are the main hurdles overall for hydrogen in the power sector? When does this get big?
Cost competitiveness is definitely number one. Hydrogen production, storage, transport. It all needs to get cheaper to really compete head-to-head with incumbent energy sources, or even other clean options like wind plus solar plus batteries for shorter durations.
Right.
Using hydrogen directly for large-scale power, still pretty early stage, lots of demos, some smaller commercial projects, but not widespread yet.
So it's not just the hydrogen tech cost, but how it compares locally.
Exactly. Commercialization depends on the tech costs and the specific regional costs of other decarbonization options. What works in one place might not be the best fit somewhere else.
What brings the cost down?
The usual suspects: R&D breakthroughs, economies of scale as manufacturing ramps up, higher utilization rates for the infrastructure once it's built, and, importantly, continued focus on safety standards and practices as things scale.
And those storage challenges you mentioned.
Yeah, they remain significant. The low density, finding suitable large-scale storage sites beyond salt caverns, the energy penalty and cost of liquefaction or conversion. These are real technical barriers still being worked on. It's kind of like where solar was maybe 15, 20 years ago. The potential is clear, but cost and scale need work.
Okay, let's quickly revisit fuel cells. You said they convert chemical energy directly to electricity. Tell us a bit more.
Sure. Think of it like a battery that doesn't run down as long as you feed it fuel. A hydrogen fuel cell takes hydrogen in at one electrode, the anode, oxygen from the air at the other, the cathode, and has an electrolyte in between.
Anode, cathode, electrolyte. Like a battery.
Very similar structure. The hydrogen splits, electrons go through an external circuit, that's your electricity, and protons go through the electrolyte. They meet the oxygen and electrons on the other side, and bingo, water, H2O. That's the only emission.
Clean and efficient. Where are they being used or targeted most?
Besides potential stationary power, a big focus now is transportation, especially medium and heavy-duty trucks.
Why trucks?
Because fuel cells can offer longer range and faster refueling times compared to battery electric trucks for those really heavy long-haul applications. That's the thinking, anyway. Still needs cost reductions and infrastructure, though.
Okay, makes sense. Now, back to grid storage. You explained the concept using excess renewables to make hydrogen, storing it, then using it for power later. Can you elaborate on how that whole cycle works, like charging and discharging?
Right. So the charging phase is when you have lots of cheap, clean electricity, mostly from renewables. You feed that power into your electrolyzers.
Okay, electrolyzers run, make hydrogen.
Exactly. They split water, produce hydrogen gas. That hydrogen is then compressed or liquefied or converted into, say, ammonia, or loaded onto a liquid organic carrier. That's the energy being stored.
Stored where? Caverns? Tanks?
Could be salt caverns for massive amounts, potentially other geological sites eventually, or in large surface tanks if compressed or liquid, or just stored as ammonia in regular ammonia tanks.
Got it. That's charging complete. Now, discharging.
What?
When you need the power.
Right. When renewable output drops or demand spikes, you take that stored hydrogen or ammonia, etc. If it was converted, you might need to convert it back to pure hydrogen first.
Okay.
Then you feed that hydrogen into your power generation technology. Fuel cells, hydrogen turbines, maybe a modified gas plant.
And that generates electricity back onto the grid.
Exactly. That's the discharge or generation phase, completing the power to hydrogen to power loop. It allows you to shift that renewable energy from when it's abundant to when it's needed.
And you mentioned maybe trading this stored energy.
Yeah, potentially. You could imagine producing hydrogen in sunny regions in summer, converting it to ammonia, shipping it to regions with high winter heating demand, and using it there. balancing energy globally or regionally.
That's a big vision. What are the most promising storage forms for this long duration currently?
Based on current tech and costs, IEA and others often point to storing it as compressed hydrogen in salt caverns or converting it to ammonia as potentially more cost-effective options for very long duration seasonal storage. But again, not widely commercialized for this specific grid application yet.
Still developing. Are there actual projects doing this power to hydrogen to power thing now? Any real-world examples?
Yes, definitely gaining traction. Remember those 500 plus projects announced? Many involve power sector applications.
Give us a couple examples.
Okay. The Long Ridge Energy Project in Ohio. Big 485 milliW gas turbine plant designed to start blending 15–20% hydrogen, aiming for 100% eventually.
Okay, blending then full hydrogen.
Intermountain Power Agency in Utah. Huge project, 840 milliW turbines, planning 30% hydrogen blend soon, aiming for 100% low-carbon hydrogen long-term. They're also building large-scale salt cavern storage nearby.
Storage included. Nice.
San Diego Gas and Electric has a smaller power-to-gas-to-power demo. Grid power, electrolyzer, hydrogen fuel cell, grid power. Shows the whole cycle.
Testing the concept.
Yep. In the UK, Equinor and SSE are planning a massive 1.8 gigawatt hydrogen-fired power station. Brazil has a project using byproduct hydrogen from a refinery for cogeneration power and heat. Energy Australia is building a 316 milliW plant designed for gas hydrogen blends. French Guiana is combining solar, battery storage, and a 16 milliW electrolyzer plus a 3 milliW fuel cell for remote power.
Wow. Okay, so it's happening. Different scales, different configurations all over.
Definitely moving from theory to practice.
And earlier you hinted electrolyzers themselves could help the grid beyond just making hydrogen for storage.
Yes.
Grid services.
Yes, especially PE electrolyzers. They can ramp their power consumption up or down really quickly. Sub-second response times in some cases.
Why is that useful?
Because the grid needs constant balancing. Things like fast frequency response helping stabilize the grid frequency if a big power plant trips offline. Electrolyzers can quickly reduce their load to help.
Act like a controllable load.
Exactly. They can also provide operational reserves, follow the fluctuating output of renewables, shift load to times when power is cheap. Basically, they can be a flexible asset for the grid operator, not just a dumb load.
That adds another layer of value.
Yeah.
Okay, shifting gears slightly, we've focused a lot on power. Where else could hydrogen make a big impact in decarbonization? What other sectors?
The potential is really broad. Road transport is a big one. Fuel cell vehicles, especially trucks and buses, maybe some cars. Rail transport, too.
Okay, transport. What else?
Buildings.
Yeah.
Potentially blending hydrogen into existing gas networks for heating, although there are safety and efficiency questions there. Or maybe dedicated hydrogen boilers or fuel cells for heat and power in buildings.
Eating. Interesting.
Shipping and aviation are tough sectors to decarbonize. Hydrogen itself is difficult for planes due to volume, but hydrogen-derived fuels, ammonia, synthetic kerosene, are serious contenders for ships and potentially planes.
So-called e-fuels.
Right. And then industry. We already use hydrogen in refining, ammonia, methanol. But it could replace fossil fuels for high-temperature heat in things like steel, cement, glass making, or act as a reducing agent in steel production instead of coal. Lots of industrial potential.
So power, transport, buildings, shipping, aviation, industry, it touches almost everything.
It really could, but it's important to remember it's not the only solution.
Right. What are the main alternatives competing in these sectors?
Well, for transport, aviation, shipping, biofuels, and biogas are options. Direct electrification with batteries is obviously huge for cars, increasingly for trucks, and potentially for some shorter-range shipping and rail.
Electrification is key.
Definitely. For power, you've got renewables plus batteries, other storage like pump hydro, geothermal, nuclear. For industry and power, carbon capture on fossil fuel plants, CCUS, is another pathway.
So a mix of solutions is likely needed.
Almost certainly. Different technologies will win out in different applications and regions. Hydrogen will likely be crucial for some, less so for others, where direct electrification or biofuels are easier or cheaper.
Okay. Given this complexity, what should policymakers be doing? How can they figure out hydrogen's best role and actually make it happen?
It's a big task for them. First step is really understanding the potential in their specific context. What industries do they have? What renewable resources? Where could hydrogen fit?
Assess the potential.
Then do the homework. proper economic analysis, environmental impact studies, look at energy justice implications, who benefits, who might be negatively impacted by new infrastructure, job creation potential.
Holistic assessments.
Exactly. Based on that, develop clear strategies and roadmaps. Where do we want to be with hydrogen in 10, 20, 30 years? What are the priorities?
Set a direction.
Then comes the support. You likely need incentives initially to make low-carbon hydrogen competitive, things like tax credits, contracts for difference,
Financial help.
and investment, supporting production projects, building necessary pipelines or storage, helping factories retool to make electrolyzers or fuel cells.
Build the supply chain.
Crucially, setting up clear rules, certification for how clean the hydrogen actually is tracking emissions. Robust safety standards and regulations are absolutely vital for public acceptance.
Rules and standards.
And finally, keep funding the R&D. We still need innovation to bring costs down and improve performance across the board. There are lots of good analyses out there from places like NREL, DOE, IEA, plus country-specific studies to help guide policymakers.
It's a comprehensive checklist. Are governments actually doing these things? Can you give examples of real policies?
Yes, definitely. We're seeing a wave of national hydrogen strategies being published. Australia, for instance, has a strategy with a clear cost target aiming for clean hydrogen under $2 per kilogram. That's ambitious.
Setting a cost goal. Okay.
Canada wants hydrogen to meet up to 30% of its final energy demand by 2050. The EU has big targets for installing electrolyzers, tens of gigawatts by 2030, and producing millions of tons of renewable hydrogen.
EU going big on electrolyzers.
France and Germany have national strategies with significant funding attached for infrastructure and R&D. India has a national green hydrogen mission. Japan has been pushing hydrogen for years, focusing on supply chains and cost reduction. South Korea, UK, Netherlands, Norway. Many others have specific targets or strategies.
In the U.S.
The U.S. Department of Energy has its hydrogen program plan, funding lots of R&D. And there's work on a national clean hydrogen strategy. Plus, the recent Infrastructure Law and Inflation Reduction Act included major incentives for clean hydrogen production.
So real policy momentum globally.
Absolutely. It's moved beyond just talk in many places.
Okay, we've covered a lot of ground. As we wrap up this deep dive on hydrogen, what are the main things people should take away?
I think first, hydrogen definitely has real potential as a low-carbon energy carrier. It's versatile.
Okay, potential is real.
Second, how it's made matters. The production method determines its climate impact, and costs vary widely. Green hydrogen is the goal, but cost is still a hurdle.
Production is key.
Third, storage and transport are critical challenges that need solving for widespread use. They're not trivial.
Infrastructure challenges.
Fourth, it can play a significant role in decarbonizing tricky sectors. Maybe power grid stability with long-duration storage, heavy industry, long-haul transport, shipping, aviation, places where electrification is harder.
Tackling the tough sectors.
And finally, while there are still big cost and technology hurdles, the global policy push and the pace of innovation are really strong. It strongly suggests hydrogen will be a significant part of the future low-carbon energy mix. How big a part and where exactly is still unfolding.
It's a dynamic picture. Okay, so considering all these potential uses, from trucking to steelmaking to grid storage and the massive infrastructure build-out needed, here's a final thought for everyone listening. What do you think will be the single biggest obstacle to actually realizing a large-scale hydrogen economy? Is it cost, infrastructure, public acceptance, something else? And maybe a counterpoint. Which sector, perhaps one that's a bit overlooked right now, might actually see the most impactful early adoption of hydrogen? Where might it break through first in a really meaningful way? Lots to think about there. It's clear this energy transition is complex. Hydrogen is definitely a key piece to watch. Thanks for joining us for this